Okay, so now we're going to take a look at another approach to making decisions. It builds on the idea of EMV, the expected monetary value that we have discussed previously, but it allows us to elaborate and understand in a little bit more detail what's involved in the decision, as well as allowing us to do something that we can't do with the EMV, and that is to look at multiple decisions. And when I say multiple decisions, what I mean is decisions that need to be made in sequence. We do one thing, something happens, and then we have to decide something else. And in a lot of situations, that's exactly what occurs. So this again gives us a structured way of understanding how we can logically make a decision. It'll give us some answers, and those answers will help us make the decision. Again, it doesn't make the decision, you make the decision, but it'll help us to understand the rationale and the parameters for making that decision. So now we'll start and look at building the tree and figuring out how do we lay it out. And this is the exact same thing that we did previously, the exact same plan that we had previously when we were looking at EMV and our plant decision. So if we look at this here, we have a decision node, and the decision node is indicated right here. We have to make a decision. Do we build a small plant, a medium plant, or a large plant? Okay, so again, if we look at the small plant, we have different probabilities, and these are the same probabilities we had on the payoff table: 0.3, 0.5, and 0.2. Okay, high demand, or excuse me, low demand, medium demand, and high demand. And we have the payoffs that we had from the decision table. If we have low demand, 10, medium demand 10, high demand 10. Exact same thing. Small plant, these are the payoffs that we have. Medium plant, same probabilities, but the payoffs are different. Low 7, medium 12, high 12, just as we had previously. And the large plant, we have the same probabilities. Low demand -4, 12, and 16. What do? We calculate across the probabilities. 0.3 times 10, 0.5 times 10, 0.2 times 10, and we have a value of 10, obviously. Over here, we look at 7 times 0.3, 12 times 0.5, plus 12 times 0.2. We have a value of 10.3. And lastly, over here, we have the large plant where we have -4 times 0.3, plus 12 times 0.5, plus 16 times 0.2, and we have a payoff of 3. So these are the EMVs, the exact same thing we had on the payoff table. And if we can see here, it says yes, the EMV of the medium plant with a value of 10.3 is the best choice for us. And we'll indicate that as we look at it. We put these two cross hatches right here, indicates that we're not going to do the large plant, we're not going to do the small plant, but we should do the medium plant. Pretty straightforward. Exactly the same thought process as we have with the EMV and the payoff table. We've just elaborated it, and so that we can see a little bit clearer what we're talking about. But the values are the same, the arithmetic is the same, and the decision logic is the same. So now we're going to start taking a look at a slightly refined version of the tree. What we're going to be able to do here is we want to be able to deal with two values. When we had the payoff table, we had one value. It consolidated multiple values, but here we can explicitly see the two values that we're concerned with. One is the cost for building the plant, and the other is the revenue we're going to receive once we do build that plant. Okay, so if we look here, all we've got the same setup as we had before: small, medium, and large plant. We have the cost 9, 15, and 20, just as we had before, and we have the values exactly the same as we did before. So again, what we're going to do here is we're going to take 20 times 0.3 plus 20 times 0.5 plus 20 times 0.2 gives us 20. That's the EMV of this situation, less the cost of the small plant is 9, gives us a value of 11. Same thing over here. We're going to take all these values, sum them across just as we had before. We have an expected monetary value of 27 off of this. The cost of the small plant is 15. 27 less 15 gives us 12. Over here again we have the payout associated with this, the EMV of 29. The cost of the plant is 20. Therefore the EMV, the final EMV for here, is 9. We look at this, we would not accept the small plant, we would not accept the large plant, we would accept the medium plant. Now if we look at this, we could also calculate this in a slightly different way. What we did here is I took the EMV of these 20 times 20 times 0.3, 20 times 0.5, and 20 times 0.2 for an EMV of 20 and subtracted it from this. Or we can also look at the cost or the EMV associated with each individual path through the network, and this is the more formal way of looking at it. So in this case we have 20 less 9 times the probability here, so that gives me an EMV of 3.3. We have 20 minus 0.9 again times 0.5, an EMV of 5.5, and 20 times minus 9 times 0.2 gives me an EMV of 2.2. If we sum these 3.3, 5.5, and 2.2, we also have 11, and we have the same value here. So either way you want to do it, it'll work out for you. But so if we're looking at here, we have 11, here we have 12, just as we had before, and here we have 9. Now in the text, for some reason, and I'm not sure why, he takes a slightly different approach to looking at the EMV, especially as it relates to the cost here. Okay, he does a probabilistic, and this is if you look on page 103 in the text. In the text, he will take this value right here, right, and calculate it in a probabilistic manner, but then he'll take this value here and subtract it totally. So he'll take 20 times 0.3 and subtract 9 from it, 20 times 0.5 and subtract 9 from it, 20 times 0.2 and subtract 9 for it. So what happens there is he is taking this value and subtracting it 3 times, so he's overstating the cost. Okay, and he mentions in the text that he does this because this is not a probabilistic number, and it's not. But what's happening is any of these times, we're not going to go and do this multiple times. This is going to happen once as we try to figure it out. We have a probability here, this is our cost here, but in this case the 9 that we have, the cost is also, we have a cost of 9 total, but we're not doing it 3 different times. So again, use this idea right here. Take the EMV of the output minus the cost associated with it times the probability, and we have the same value here, right, as we sum these as we do here. So it's a little bit confusing, and we'll go over this when we look at some of the problems. I just didn't want you to get confused, as I know you're all studying the text and trying to figure out how they all fit together. But again, so this value here does not get subtracted 3 times, right? So 3 times 9 would be 1827. It's only subtracted once because we're only going to build this plant 1 time. We're not going to build it 3 times. Okay, so now we are going to look at a problem where decision trees become much more valuable and much more insightful and allow us to make decisions or understand our decision making that we can't just get from the payoff table. Here we have a situation where we have to make multi-stage decisions, and we're going to do this step by step. So the first thing we're going to do is we will build the table. So all of the information you see here is information that we would need before we started getting into the problem solving thing. So we have a company, and this company has an option. It can bid on a school or it can bid on a garage. Okay, bid on the construction of the school, bid on the construction bid on the construction of a school, or bid on the construction of a garage. In order to bid on the construction of the school, it's going to cost them $8,000. Bidding on the garage is going to cost them $12,000. Okay, no big deal. One is more complex as far as the bidding process, so it costs a little bit more money. If they bid, there then is a chance. We have no control over this. We can either win or we can lose. Okay, there's a 70% chance of winning. There's a 30% chance of losing. With the garage, we have an 80% chance of winning. We have a 20% chance of losing. If we lose, it stops right here. Okay, we have zero value attained from this. So therefore, we've just blown the $12,000 on the garage or the $8,000 on the school. So that's where we stand with that. Now, if we do win, we have to make another decision. This is our personnel package. Will we put in our A team, that is our more experienced team, and that team will cost me $30,000, or will I put in my B team? They're going to be less experienced and they're going to cost me half as much, $15,000. So do I put the A team in there or the B team? If I put the A team in there, I have these different probabilities for the outcome. If I put the A team in there, I assume I have a 40% probability of making $100,000, a 60% chance of making a $50,000. If I put the B team in there, I've got a 50% chance of making $50,000 and a 50% chance of making nothing. Likewise, on the garage, we have a different set of values, but we still have the same cost for the A team and the B team, and we do have different probabilities. So if we put the A team in there, I've got a 50% chance of making $65,000. I have a 50% chance of making $60,000. If I put the B team in there, I've got a 40% chance of making $60,000 and a 60% chance of making $50,000. Obviously, the payouts here are much tighter than the payouts up here. But again, we have now just laid out all the information. Again, all of this information here, everything that you're seeing on this page is something that we would need to have worked out before we decided to make our decision. And again, the GIGO principle holds. This is obviously, as you can see, is a little bit more complicated. If our information is good, if our decision-making criteria is applied correctly, then we'll have something that will give us a good potential direction as to how we should go with our decision. So now we have the second stage of the decision-making criteria. So now we have to start making some calculations, and this will help us make our decision. So when we make the calculations, let me get my little pointer, my laser pointer, there we go. When we make the calculation, we work from the right-hand side to the left-hand side. We start over here and we work here. So the first thing we're going to do, as you can see here, is we're going to take the probability, we're going to take the probabilities and we're going to multiply that times the payoff. So 100 times 0.4, 50 times 0.6. That is the value of the potential payoff that we have. And in order to get that, I have to use my A team, and that A team is going to cost me $30,000. Therefore, the EMV for this approach is going to be 50. Over here, I've got 50,000 times 0.5 and 0 times 0.5 less the 15,000 right here. So the payoff at this point is going to be 10. I would not logically ever pick the 10,000 over the 40,000, right? This payoff here is higher than the payoff here. Therefore, logically, I would take the option of bringing my A team in, and I would not look at bringing my B team in. I would never take less than more, all else being equal. We did the same thing over here on our bid on the garage. 65 times 0.5, 60,000 times 0.5 minus the 30 gives me a value of 32,500. Over here, I've got 60,000 times 0.4, 50,000 times 0.6 less the 15,000 gives me 39,000. So in this case, we now have a situation where the B team returns the greatest EMV. We've got a $39,000 EMV if we bid on the garage using the B team, and we've got a $40,000 EMV bidding on the school if we use the A team. Again, logically, I would never pick the smaller choice. Therefore, I need to continue my analysis using this and using this. Those are the two values that I'm going to go forward with. And I'm going to look at bid on the school with the A team, bid on the garage with the B team. So now we're going to keep working from right to left. So here again, we don't care about this track anymore, and we don't care about this track anymore. Okay, these no longer are of interest to me. I'm only going to look at this track right here. So I've got a value of $40,000. Okay, however, there's only a probability, a 70% probability of this occurring. Therefore, the EMV at this point right here is $28,000. Over here, I have a EMV of 39,000. The probability of my winning is 80%, 39,000 times 80. So here I have a value of 31,200. So now I've gotten to the point where I'm looking at the cost for the garage and the cost for the the cost for the school and the cost for the garage. So now I just need to go, I've got the EMV all the way to this point, right? Now I just have to go back and look at what the specific costs are associated with the bid and how does that affect my criteria. And again, moving from right to left. And again, on the losing, there's a 30% probability. However, there's zero financial implications to that. 0.3 times 0 is 0, so I don't bother factoring that. 0.2 times 0 is 0, so I don't bother factoring that in either. And now we can make our final decision as we look at it. So here we've got a value for the bidding on the school of $28,000. We have a cost of $8,000. 28,000 minus 8,000 equals $20,000. Over here we have a value of 31,200 if we were to bid on the garage, but it's going to cost me $12,000 to do that. Therefore, 31,200 minus 12,000 equals 19,200. What should I do? In this case, I want to again take the EMV, that's the highest, the expected monetary value, that's the highest. So what I'm going to do is I will bid on the school, spend $8,000 with the expectation that I've got a 70% chance of winning. I will have my A team do it with an expected monetary value of $40,000, but the value for the entire sequence that we have right here is $20,000. Same thing over here. We look at it, we have a value of $19,000. So this is going to be my preferred choice. Now, interestingly, if I wanted to take this and think a little bit more deeply on it, yes, I can do this and make this going forward. However, if I have the capability of bidding on both the school and the garage, right, I could bid on the school, have my A team work on it and expect to make $20,000. I could bid on the garage and have my B team work on it and have an expected value of $19,200. So theoretically, the way I've set this up allows me to make a decision. Not only should I bid on the school or bid on the garage, but also seeing that can I actually do both of these activities. If I only have one A team and one B team, if the A team was a superior, was involved in the superior outcome in each of them, I could only choose one. But here we have the situation where I have the A team on one, the B team on the other. As long as I had the capability of doing both those bids, I should theoretically probably try to do both of them. So again, we can go and just follow the branches and we should come up with the same value as we just discussed previously. So if we take the EMV of the A team for the school, we have 100 minus 30,000 times 0.4, 50,000 minus 30,000 times 0.6, which gives us 28 plus 12 or 40,000. The probability of us doing that is 0.7. 40,000 times 0.7 gives us 28,000. 28,000 less the $8,000 cost gives us a value of 20,000. The EMV of B for the garage, 60,000 minus 15 times 0.4 is 18,000. 50,000 minus 15,000 times 0.6 is 21,000. Gives us a value of 39,000. There's an 80% probability of that. Gives us 31,200. 31,200 less the 12,000 that's going to cost us to bid gives us a value of 19,200. Again, the exact same thing as we had on the previous approach. So if we look at it, then either way, these are the values that we come up with. Obviously, based upon straight EMV, as we discussed, 20,000, we would take EMV of A team and do the school. If we had to make a choice for one versus the other, with the garage, we're looking at an EMV of 19,200. Again, the choice gets to be up to you. Obviously, as we discussed previously, there's greater variation. With the building of the school, we have a greater upside, greater downside. With the garage, it's a much tighter confines. You could factor those in, but based strictly upon a logical EMV approach, you would pick the building the school and applying your A team for it. So again, we've been able now to sit down and figure out, based upon a not a multi-criteria, but a multi-step decision process, which is the best approach given the information that we have here. And again, as we talked about, the 20 versus 19.2 may not be that much of a factor, but all else being equal, we would pick EMV or the A team for the school.